We all understand the central role DNA plays in information storage and transmission, but we often don't consider what this implies about its physical structure. DNA is constantly being coiled up and ripped open and unwound. This means it has to be quite a dynamic molecule. It's worth exploring how it does this, because that can shed light on the mechanism by which it binds to drugs and regulates genes. At first glance, it may seem impossible to model a system with so many molecular components, but we do this in the real world all the time. Engineers modeled the behavior of steel using just two numbers, the bulk modulus and shear modulus. They don't need to know the details of its atomic structure, because at our scale, we don't see a collection of vibrating atoms. We just see a continuous rod that can resist deformation. In other words, a complex system can be described by just a couple parameters as long as we zoom out sufficiently far. However, this only works if the system has a uniform structure, like a beam or a fluid or a bilayer membrane. It wouldn't work on a protein, for example, since it's composed of different monomers. So why are we justified in applying this phenomenological approach to DNA? A DNA molecule is about 2 nanometers wide, but it's 2 centimeters long. So on the scale of its length, the internal mechanisms become irrelevant, and we can approximate it as a sort of flexible cylinder. Our first step towards building this model is to define the parameters. We have an idea of DNA as a elastic rod, so let's think of a macroscopic object that reminds us of that, such as a garden hose. We'll call the smallest unit of length ds. If we elongate the hose by an amount delta ds, the stretch u is the fraction of our fundamental length that the hose has been extended by. We can also bend this hose. Bending is simply changing the tangent vector. At a distance s from the end of the rod, the tangent vector is t. If we take a step ds along the bend, then the tangent vector changes by dt. So the bend beta is dt ds. Lastly, we can twist the hose. If we call the vector along the radius phi, twisting by the unit length ds would cause a unit rotation of d phi. So the twist density omega is d phi ds. Now how do we map this to DNA? Each base pair lies in a plane. So the bend is how much the plane is tilted. A base pair is 0.34 nanometers thick. So a segment of n base pairs are ordinarily n times 0.34 nanometers long. The stretch measures how much longer the segment is than this length. This segment will complete one helical rotation every 10.5 base pairs. That means 2 pi radians per 10.5 base pairs. Multiplying by the thickness of each base pair tells us the length traveled along the helix for every radian turned. The twist measures the change in this quantity. Let's say we twist the helix and get a new rotation per base pair of delta psi. Multiplying by the length per base pair gives us the new length per radian turn. The difference between the two is the twist. We have quantified 3 ways of deforming an elastic rod. If the deformations are not too big, we can assume Hooke's law applies. So the total elastic energy required to distort the system is proportional to 1/2 times the square of each distortion. This term arises from the fact that we can twist and stretch the rod simultaneously. The reason we don't have a twist and bend term or a bend and stretch term is because that would be a vector, and energy has to be a scalar. On that note, if we want this expression to produce an energy term, then we need to ensure that this whole mess has units of joules. The easiest way to do that is to multiply each factor by a constant with opposite units, so they cancel. Then we multiply the whole thing by a constant with energy units. The standard thermodynamic energy factor is Boltzmann's constant times temperature. You can think of this as the energy from the ambient thermal motion of the surrounding molecules. Let's say we've got a polymer composed of single bonds. That means the monomers can freely rotate, so there's no twist elasticity, and these terms drop out. Also, when we distribute, one of the terms will have Boltzmann's constant times temperature times B. This has units of joules per meter, which is just newtons, meaning it's a force term. So as long as we pull with significantly less force than this quantity, then the stretch term is negligible. So all that's left is bending. We said beta is the change in the unit tangent vector. So if a segment ds is bent through an angle theta, then the magnitude of beta is d theta ds. An arc is related to its angle by the relation ds equals r theta. So beta is 1 over r. If we integrate over the total length, plugging in our expression for beta and integrating over the total length will tell us the energy required to bend a polymer by a certain angle. So let's find out the energy needed to bend it into a quarter circle, or 90 degrees. Since everything is a constant, we're just integrating over the length of the quarter circle, which is the circumference 2 pi r divided by 4. This gives a very interesting expression. The energy required to bend a polymer into a circle decreases with the radius. In fact, if the radius is significantly bigger than a, then the energy of the surrounding thermal motion is enough to coil the polymer by itself. This seems bizarre. Pulling on a chain of paper clips doesn't cause it to spontaneously coil up. But if we put it on a vibrating table, then it definitely will. If the paperclip chain is a polymer, then the shaking is the incessant thermal motion of the surrounding molecules. A straight polymer will definitely not remain that way because the constant kicking will force it to coil up. Now, this model we derived is not the complete three-dimensional one, but researchers have conducted experiments in which they stretch a strand of DNA to get a curve of length versus force. And the 3D version of this model fits the curve pretty well. So this serves as a good foundation to build models of more complex behaviors, but we'll save that for another video.